I'd like to introduce our next speaker, who is Jonathan Henry, formerly of John Deere and now director at Garford Farm Machinery. Welcome to you, Jonathan.
Welcome, Olivia, and thanks to the Institute of Ag Engineers for the invitation to join this conference. And I'll just share my screen here. Okay, so this next few minutes here, I'm going to talk about a real-world case. So I'm going to really scale this back from the global picture with AI that's just been covered by Fernando into a real use case of AI in agricultural machine control. And it's one here that we've been working on for the last 6 or 7 years, and we've just deployed the first machines into customers' hands in 2025. Just a little bit of background on Garford Farm Machinery. So we're a small business. We started manufacturing equipment in 1986, focused primarily on sugar beet harvesters at that time. The business is now owned by a German family called a guy called Rolf Zern, which the business is Zern Harvesting, and that's been the case since 2019. The sugar beet harvesters, we stopped production of that in 2006, but we started and transitioned into vision-guided hoeing systems in the early 2000s. Our first inter-row machine was put in the market in 2001. We then also released an in-row version of that in 2012. And then in 2025, we released the first Robocrop AI machines into the marketplace. It's not the only innovation we're doing at the moment. We're also working hard on electric weeders and taking high voltage electricity as a weed control agent into the marketplace. We've got some of the first machines in the market in 25, and we'll have more of those in 26. We're a UK-based company just at Market Deeping, just above Peterborough, and we do everything here from this site. And also, we're chasing quite a specialized customer segment around the world. So therefore, for the business to work, we need to export, and that's always been the case from the beginning. And actually, in a number of years, our revenue has exceeded 90% of our revenues come from export sales, and we've got sales in over 25 countries. However, the bulk of those, the biggest markets that we've served in the last years has been France, Germany, but also California, and more we're putting machines also into China and various other markets as well. So we're very vertically integrated. We do our own engineering. We do a lot of machine configuration to make it fit the customer segment, and we do it all from here. Okay, so just to get this warmed up a little bit is if you're going to take a product or a technology into a solution that's commercial, then you need to understand what your market drivers are, and these are the key ones. And these apply to all of our business, not just the Robocrop AI component. But first of all, organic production is a key segment for us. Not everything we do goes into organic, but that's a key segment given the constraints they have and being unable to use synthetic pesticides. That's obvious. The next key one then is cost of labor. Hand weeding has become more and more expensive. Not only that, it's much more difficult to get the people that want to do that, and then you need them, and you need them to work really hard for 5 or 6 weeks a year, and then you don't need them. So that's a major challenge, and that provides ultimately the economic headroom for mechanized solutions, certainly in the organic space. The other piece is, as we know, farmers are losing active chemical agents that they've relied on for the last 80 years are becoming less and less, not more. And although there are still some new actives in the pipeline, that's nowhere near at the level of the deletion of those actives. So there is a net reduction happening there. And so that's driving a couple of things that are going on, and I'll come back to one of those in a minute. The next one then, there's less actives, but there's also, let's say, some challenges around the way those are used. and farmers are seeing around the world more and more challenges with selective herbicide resistance. In fact, a few years ago, I was in a global survey about the future of agriculture and agricultural mechanization. And after labor availability, consistently, and this was in all regions, North America, South America, Asia, the second highest concern that farmers had was resistance to herbicides and what they're going to do in the future to navigate that. And these things all kind of come together, and to make the systems that are deployed today sustainable, there's a real crisis. Because if you're using chemicals to control a pest and you have less and less tools as a farmer in your toolbox, then more and more often that a single vector control ends up being the result. And that's the very worst thing you can do to encourage more resistance. So we see more and more advanced farmers actually remembering what they learned at college and university, which was never control a pest with a single vector, and rethinking that. And we're seeing conventional farmers looking to add alternative weed management techniques into their portfolio, into their strategy, and looking at alternatives to make at least those actives that still work on their farm, to make them last longer in their own production system. If we move on then to Robocrop AI and what are some of the customer value drivers for that, the first one is the guidance systems we use and we still use today are with Robocrop Original was a green on brown system using color and a grid matrix. With the green on green system, then we are able to deliver a solution to that farmer with a wider operating window. So agronomically, it's still best to manage the weeds as early as possible. That's still the best outcome, and that's the desired target. However, the weather conditions, field conditions don't always allow the treatment to happen at the optimum timing for that. And a green on green system provides risk management to the farmer or the producer in widening that operating window. The next piece is about precision, and with our AI system, we're using multiple methods to scan the images that we're harvesting from the crop, and it allows us to get a very, very high precise stem location, which ultimately that's the key piece in a hoeing machine, because if we have that precise stem location, we can treat the weeds really, really close to the plants. They're the ones that are most important to get, and ultimately get a higher efficacy of weed management. And then the third one is in terms of resilience, with a vision system where we're using the solar or sun as the primary light source. Then there can be some challenges when we use color only, and with a multi-modal camera system and a processing mechanism that looks at multiple different characteristics, then we've got better resilience in varying light conditions. Ultimately, the combination of these things delivers us the potential for a higher performance solution for the customer, higher availability for machine usage, so therefore lower risk in transitioning to this type of system, and ultimately that leads to cost of operation improvement. So those are ultimately the benefits for the customer. Quick overview then of a Robocrop AI system. So first of all, if I look on the top left here, we've got some cameras. These cameras, I'll talk a bit in more detail about those in the next slide. But they are mounted in front of the machine and looking down at the crop. And what we want to do is we want to find the lines of crop, and we want to find the individual plant, crop plants, and identify the stem location. That's the goal. That's the job that we want this system to do. The next item then is the ECU, which is mounted in this white box here, but there are multiple elements within that. The first one is we're using a convolutional neural network here, and that needs to be running on a processor, and it needs to be a very high performance processor compared to those that are typically deployed in mobile machinery. And I'll come back to that one in a moment, but that's housed in this box. We also need very strong data communication between the cameras, and for that processor, for that we use Ethernet, because only that will give us the data flow speeds that are necessary. And we have to also harden up those connections, because most of those systems are designed for internal use or office environments, not for field environments. Also in that box, we have our machine controller, which ultimately takes the locations, the plant locations and stem locations that are processed, and turns that into the outputs that we need to ultimately control the machine. And then we do the piece where we control the rotor, which we'll come to in a minute. We do that over CAN. So we've got multiple different communication networks deployed here, matched to the capacity that's necessary for the data flow, and also the machine control using systems that are robust and deployable. We have a display in the cab for the operator. In this case, this is a virtual terminal, so it's sitting there. There's a picture, I'll come back to that in a moment. And then on the hardware of the machine, we've got an implement. In this case, it's front mounted. Normally that's how we do it, but we can put it on the rear as well, especially for the US market, where they don't often have front hitches. But we have what we call a free shift mechanism. So the tractor is providing propulsion. It just pushes the toolbar down the field. And when we're actually in work, that system is free to float left and right, and is completely controlled in terms of its position by the disc steering and leveling system. So we're not just steering the unit precisely on the rows using our disc steers, we're also actively leveling the toolbar, because when we're using mechanical weeding, the very precise control of the depth is an essential component as well. Not deep enough, we don't treat the weeds properly. Too deep, and we're potentially moving more soil material than would be desirable. And then at the end of the day, once we've tracked the lines of crop and got the steering position correct, then we need a e-rotor here, which is a high performance, high torque stepper motor system. And we need to then control that and manage the exact precise position of that, because that's the tool that is doing the weeding between the plants. And ultimately, the quality of the work and the job done comes down to that precision of that control. So that's a very, very brief overview of the total system. I'm going to dive a little bit now into the components we're using. So first of all, we have a camera. The camera in the Robocrop AI system is a multimodal camera. So this gives us many, many more options. So it has stereo NIR cameras here, which allows us to measure depth at a very, very precise way. But it also allows us to identify stems, and most importantly, the stem conversion point. And that stem conversion point is ultimately what correlates to where the stem connects to the root and the soil, and that is the point that we then want to precisely hoe around. We're also using color camera from this unit, so we still use color, and we use that as well for leaf shape profile, so that we can distinguish between crop plants and non-crop plants. Currently, we don't do any labeling for non-crop. It's either a crop or it's a non-crop. We don't care which non-crop, or if it's a crop plant that's in the wrong place, then again, that's, you know, we treat that as a weed in our system. The camera also has a laser emitter and sensor as well. And ultimately what we're doing is we're harvesting the multi-modes of data being harvested real time with high resolution and we're feeding that back through into the processor, which was running a convolutional neural network, and that's the AI piece. So these are convolutional neural networks are highly developed tools, been around for quite a long time. But what we're doing here is we've trained this network or built this network specifically to do the job that we're aiming to do, which is find stem locations of plants and rows of plants. And that is running on a high performance processor. We use an NVIDIA unit for that, and we're using the Jetson platform, which is pretty much what the majority of these types of systems are using, although there are other options more and more in the marketplace. And then after we've done that, we need to then actually control the machine, right? So this is more conventional, but we've updated the technology we're using here significantly, and we've got to get steering controls out to our implement to precisely steer that toolbar, to manage the leveling system, and also to communicate to the e-rotor its target position as it's working its way down the field. And of course, in multiple rows, we will have multiple control streams running to each one of those rotors. And we've built machines up to 24 rows, which are deployed in California, and that's quite a lot of data flow and data management to be handling. So that's quick overview of the hardware components. In terms of the user interface, that's also a very important piece, and because the operator needs to have confidence in what they're doing. This we also have done ourselves. That wasn't the original plan, but this is a shot of our main run page here. So we have things that we've had before. We've got side shift positions, so the operator can see if they're well within the operating range of the machine system. We'll provide a live stream of the camera images to the operator, because especially in the early stages of adoption and training for the operator, we find that brings a huge amount of confidence to them. However, in reality, when the system works and does what it's needing to do with high reliability, that's not really necessary, but it's something that we find users and customers desire. And then we arrange shortcut keys for machine optimization and setup that are in the layout as described. And we also provide a bar graph on the left-hand side in terms of the network performance, so that the operator can see is the network performing at a level that is high confidence or medium confidence, and that also gives them an understanding of how that's working without them necessarily having to monitor each and every plant in real time themselves. Okay, some of the results then that we're seeing from the Robocrop AI and how that differentiates. The first one is if we're using a color only system, then sometimes distinguishing between crop and broadleaf weeds that look very similar to the crop can be quite challenging, and the network with multimodal processing is very highly successful at managing that and making that decision and doing that correctly and precisely. And then also, in addition, finding that exact stem location, which is represented here by the yellow dots. In terms of crop plant overlap, again, a color only system when the plants get larger, or if they're planted quite close together, which is often desirable from a weed management in later growth stages. Then when we have overlap, then sometimes a color match system can pick the center of the color mass, which is actually neither the stem of the first plant nor the second plant, and then that can lead to misses in the system. And the Robocrop AI is able to distinguish between those and still find the exact center of the crop plant. And so higher availability of use at later growth stages. And then the bottom left is showing a green background. That's not the most extreme one, but again, when we've got high weed pressure, where perhaps entering the crop didn't happen at the optimum time, then we've got a system that's more resilient to that. This is not a recommended practice, I say here, but if you look over in the top right, an extreme case. And I wasn't brave enough compared to some of the later speakers to actually run a video live stream of this over Zoom, but you can see a crop here which is really out of control, right? So a brassica crop where in an organic system where whatever reason the producer, the weeds got ahead of him, and he thought it was unrecoverable. And we were there, and we put Robocrop AI into that crop, and we were successfully able to find those plants, weed around those plants, and clean that out. And the picture at the bottom is immediately after the tractor passed. In fact, the tractor tire may even just be visible there. So this is a game changer in terms of vision control systems, steering hose, and it's an extreme example, but it's an example of what the system has the potential and is capable of. In terms of business and engineering challenges, when you want to deploy this type of system, then for us at least, this was new specialist skills that we didn't have in-house, so we had to acquire those, and that's very, very specialized. It's unlikely that you're going to have that in a more traditional engineering farm machinery company, that's there pre-existing, so you're going to have to find those specialist skills and integrate them in. And that's a clear challenge. The next one that I put on here, by the way, these are by no means all the challenges of deploying an AI system, but they're the three that I picked as being ones to specifically mention. The second one here, scope management. So this audience will know better than anything that in any engineering project, scope management is an essential component. You know, get it wrong and the project will fail, or it'll overrun, or it'll miss its goals or miss its target. But I would say more than anything else I've ever seen, and I've worked on many, many engineering projects over my career, in an AI project, getting the scope management right is absolutely essential, because you can't say no scope change, because you're working with new stuff, you're learning things as you go. So you can't say zero, because that won't lead to the right outcome. But I think the challenge here is with new technologies, not always a total understanding of what's even possible. You get the engineering team gets, well, it's help, yes, but it's ideas for new ideas, which are all good, but if you don't really manage that and decide which of those you're going to add to the program scope with very high level of intentional intent, then you will delay, you'll overrun, you'll miss your goals, and you'll end up in remorse. So I think scope management is the absolute number one component in terms of getting this type of system up and running and deployed. And then the third one on here is CNN. So a convolutional neural network has to be trained. And so that training, there's a lot of that training you can do in advance. So we have networks that are pre-trained for crop groupings, salad crops. We have a network, we have a brassica crop network, we have a sugar beet network. However, you can get in the field and find conditions that are different to what you trained for, and it may need optimization. And one of the big challenges with a AI system is, how do you fund that training? How do you get commercial coverage for that? Do you build it all into the upfront price of the machine, or do you have a recurring revenue model where you charge for that as you go along? How do you do that? That's a huge task and a huge challenge. And the other piece is the workload demand for that training typically comes in season. So it comes in the use season. We're in a seasonal business, so all the work demand comes at the same time, and you need specialist resources to do that training. That's one of the challenges from a business point of view in the whole business model for this type of system. I think this is my last slide here, but it's about going back to the title of the conference, and I just put a few thoughts together in that regard. I apologize, this is not livestock based. This is thinking about mechanization and labor in arable systems. You know, will artificial intelligence revolutionize agriculture? We think about that here. Yes, we believe absolutely AI tools will be transformational, are already being transformational. There's many examples of that. But if we split it, we think that machine control is one area, and that's the example with Robocrop AI as a machine control system where it's replacing alternatives that pre-exist with a system that can do it better for the customer. We also think about job optimization as another area where AI has a potential opportunity to play a role. And if you think about farmers and farm managers, what do they really do, right? They really, in the end, they're managing labor and machinery, or at the end of the day, they're getting jobs done, but it's a balance and a mix between labor and mechanization. And for sure, there are opportunities there for optimization because that constitutes a significant chunk of their cost. And lastly is agronomic optimization. And this is the one where the economic headroom is by far the greatest, but and will AI tools have a role to play here? Absolutely. But if we think about this machine control, job optimization, agronomic optimization, the economic headroom gets greater as you go down that list. But the challenges of getting that in the hands of an end user, farmer, producer, grower, in a way that they can deploy it and turn that into benefit for them get greater as you go down the list. So with that, I think I'll maybe just pause and say, are there any questions?
Jonathan, thank you for that. We have lots of questions, you'll be pleased to know. That's incredible technology. Lots of questions about the practicalities of real world examples and how this is actually being used in the field. So questions around how this technology handles with unfavorable weather conditions, uneven terrain, examples of how components can be rugged enough for real world use examples. So just talked about the practicalities of how this is being used on the ground now.
Yeah, so this is the thing that frustrates farmers a lot is they see all these ideas about how the AI systems and technology in general can help them, but when they buy it, they want it to work. Not just want it must work. It's not a case of it might work or it might be better and then stop again. So yeah, deploying that and getting the systems rugged enough for real world farming environments, which especially when you're working with higher voltages or you're working with precise control systems, you know, many of the hardware components, etc., are not when you acquire them, they're not ready for that environment. What agriculture does, especially with dust and moisture, is very, very different to controlled environments. So that's a big part of what we need to do as we deploy solutions is ensure that is robust, and it's about testing and verification and more testing and verification, and that is an essential component. And if we don't deliver that bit, then you know the customer won't they won't invest.
Okay, and how different would the architecture or specification of the Robocrop be different if it was built for a fully autonomous tractor platform? That question
Actually,
from Thomas.
it wouldn't be very different at all, actually. In fact, we do already have some systems deployed on, let's say, I wouldn't call them fully autonomous. I'd call them remote operator monitored. But they are, there's no operator on board, and we have systems in already deployed in some of those types of vehicles.
Thank you. Big question that we can discuss more in the panel later as well, but some years ago there was a view that agricultural equipment dealers and agronomists were probably best placed to be the system integrators of new technology for farmers. Do you think that education and adoption has happened quickly enough, or do you think we need to think about a new model?
So I think that this is an area where we all need to look at ourselves here as an industry. You know, Mark talked earlier about when he started with yield mapping, and I also have worked on numerous precision farming projects over the last 3 decades. And I think as an industry, we've failed because in many cases, the farmers have invested in the hardware, they've invested in getting the software in their farm office, and they've now got data flowing at them at a rate they could never imagine, but they've still failed to unlock, in most cases, they've failed to unlock the economic headroom that sits. It's still sitting out there, even though they bought the equipment to do it. And the bottom line is more information doesn't necessarily make the decision making easier unless you've got good tools to interpret that and make it simple to make those final decisions. And if you leave the farmer as the system integrator ultimately of that, then it fails. So as an industry, that's where there's a big gap there to close, and our track record on it, I would say, is per.
Thanks, Jonathan. I think one more question. So you mentioned sustainability there. There's a couple of questions on that. What measurable outcomes are you seeing in terms of water usage and fertilizer application, etc.? And someone's commented, you know, will we see mechanically weeded on farm by AI on our food labeling in the future?
I'm not aware of anybody that's using that as the go to market for the end product, but obviously there's existing labels, organic and others, sustainable, where that technique is integrated. But I think that regardless of the end consumer demand, I don't think end consumers are going to ask for mechanical weeding. But what processors and retailers are asking for, these systems and these techniques fit into their strategies of what they want to see in terms of they don't like manual labor being used the way it is because they see that as a risk, and farmers don't like it because they see it as a cost. And so the drivers are there, but I don't think it will be on the label of the end product on your supermarket shelf anytime soon.